All right, so this last video on Unit 1 is all about projectile motion, which is really just motion in 2 dimensions. So when you launch something, when you throw something, you want to go projectile motion. So really it's a combination. Projectile motion is just kind of the combination of everything we've talked about. When we look at motion in a couple different dimensions plus free fall. All right, and here it is. The projectile is an object that moves in 2 dimensions under gravity and nothing else. So the moment it leaves whatever it launches, when it launches it, it's a projectile. Okay. For the most part for this, we're going to neglect air resistance. Obviously there is air resistance to slow it down, but for this, we're just going to ignore it. All right, so we have two different objects. Okay, one ball is launched vertically. One ball is just dropped. Okay. From the moment that they're hit, after they're hit or released, gravity is the only thing affecting them, so they will fall at the same rate. So they're going to accelerate downward at the same rate, which means they're going to hit the ground at the same time. Okay. Yes, the yellow ball is going to end up farther away than the red ball, but if they're dropped and launched at the exact same time, they're going to hit the ground at the exact same time. Because the only thing pulling them to the ground is gravity. The only thing accelerating them downward is gravity. And they're both accelerating downward at the same rate, 9.81 meters per second squared. Okay, so now if we look at the vector components of this, okay, we have acceleration is always downward at the same rate, negative 9.81. However, the velocity vectors change as they go. Okay, from the release point, there is a downward vector and an angled upward vector. So your net component is actually downward. Okay. So as you go up, the angle vector decreases because you're actually slowed down vertically. Okay. All right. Now the interesting thing about projectile motion is the horizontal motion remains constant. There's nothing slowing down the object horizontally. It's just that gravity is accelerating it downward vertically, so it's going to slow down as it goes up vertically. Speed is up as it comes down vertically. But horizontally, its velocity horizontally doesn't change. So that's why it says here the horizontal component of acceleration is 0. All right? So we have a launch angle. Okay? The angle that it's launched above the ground. So we have an initial velocity here that's made up of a horizontal launch speed and a vertical launch speed. Okay, because as it's going at an angle, there's going to be some horizontal, some vertical launch speeds. The horizontal speed, as I mentioned earlier, remains constant. The vertical launch speed, or the vertical speed, changes. It decreases as the ball goes up. At the very top of its path, it has 0 vertical velocity, and it increases as it comes back down vertically. For vertical velocity, horizontal velocity doesn't change. Okay, so again, here's the path of the ball. All right, we have this launch speed. We know the horizontal and vertical components of this speed. Okay, every second, vertically, it's going to get this much. It's going to get 9.8 meters per second of speed less as it goes up. So after 1 second, it's lost 9.8 meters per second squared, or meters per second of speed, vertically. Horizontally, it remains constant. At the top of its path, it has no more vertical speed. Okay, then as it comes back down, it's gaining that 9.8 meters per second of speed vertically again. Horizontally, the speed remains constant. Okay, notice, from this point to this point, my speeds are the same. They're just going in different directions. Okay, because this is like what we mentioned before when we throw a ball up in the air. Okay, from here to here, it's gonna take a second just to slow down at the acceleration due to gravity As it comes back down, same rate, acceleration due to gravity. Then as it comes back down another second, the speed going down is the same as the speed going up initially. Okay. So this is something you're going to need to look at and understand. Okay. So again, if you have an object that's launched, if you know the angle and the launch speed, you can figure out the horizontal and vertical components of those speeds. Okay. Again, after launch, the vertical velocity decreases as it goes up, increases as it comes down, because the acceleration due to gravity is constantly downward. But notice how the gaps are equal. Okay, the horizontal velocity never changes. It has no acceleration horizontally. So we're going to use the kinematics equations when we use projectile motion. Okay, the nice part is G can be substituted in for acceleration, because it's all we're dealing with is acceleration due to gravity. So we're going to use these formulas to figure out whatever we need to know for our projectile motion. So let's start looking at some problems. Okay, so again, we know that AX is 0, we know that AY is G on Earth. Okay, so now we're going to have to solve some problems to figure out how to do this. Okay, now, for the horizontal component of our speed, we know Vx is constant. Okay, so then if we know our time, we can figure out our final horizontal speed, or excuse me, our final horizontal displacement, because our vertical speed, our horizontal speed is consistent. Your vertical speed changes. Slows down as you go up, speeds up as you come back down. But G is consistent. So if you know G and you know T, you can figure out various things. What you can also figure out is if you know the initial velocity, at the very top of its path, Vy final is 0. So you can figure out how long it takes to get to the top of a path, which is typically halfway through the path of the object. Okay, so we're not going to launch things right now. They're going to go off a cliff and fall. Okay, so we have this dog running off a cliff. It could be rolling a ball off a table. Same basic idea here. Okay, so dog runs at a speed of 8.5 meters per second straight out. Off the end of the dock, that is 0.61 meters above the water. We want to figure out how far does the dog go before splashing down. So we know we have no initial horizontal distance, no initial vertical speed, because he's running straight out, so there is no initial vertical speed. Ti initial time is 0. Your Y initial is 0.61. Your Y final is 0 because he hits the water. AX is 0. AY is negative G because he's going downward and he's going to speed up. Ultimately, we're looking for this distance here. Okay? So we know that initial velocity is 8.5 meters per second horizontally, and vertically the initial speed is 0. Okay, and we know that really the other big number is we know that he's 0.61 meters above the ground. Okay, so because the dog is 0.61 meters above the ground and we know acceleration vertically is G, we can solve for T. Okay, so we know Y final is 0. We know our initial height is 0.61 meters. That's where we started. He has no initial speed. Okay, so we don't have to worry about the initial speed piece at all. Then it's 1/2 acceleration to gravity times your time squared. Okay, we rearrange this, and we get T is 0.35 seconds. That means he's in the air 0.35 seconds. So that means to go from here to when he hits the ground is 0.35 seconds. So we know then, because we know that he's in the air 0.35 seconds, we know that its initial speed is 8.5 meters per second horizontally. And so then we can figure out, because distance is speed times time, we take 8.5, which is your speed, times 0.35, which is your time, multiply them together, and you get a distance of 3 meters. Okay, that's how you solve a problem when the object is launched horizontally. Okay, now it changes when things start to get launched at an angle. Okay, when you launch on an item at an angle, now you have to look at its initial launch speed, which has a horizontal and vertical component. Okay, so we have this problem. A grasshopper can jump a distance of 0.76 meters from a standing start. Okay, if the grasshopper takes off at an optimum angle for maximum distance of the jump, what is the initial speed of the jump? Well, if we look at this, the farthest distance can be achieved at 45 degrees. Okay, so if we know that we know that the angle is 45 degrees, we can figure out the initial speed. So for letter A, here's how you solve it. So you know the total range is 0.76 meters. So the highest point of the arc is halfway there, or when x is equal to 0.38 meters. Now here's why that's important. At the midway, okay, the midway point is where your y velocity is 0. So if you can figure out how high above the ground that y velocity is, then you can figure out how long the object's in the air, which then you can figure out the initial speed. Okay, so we know that this holds true. Okay, so 0.38 meters in and 45 degrees, which means that the vertical is about that same height. Okay, we can use our kinematic equation. Vy final is equal to Vy initial squared plus 2ay. Our Vy final squared is 0. Our Vy final is 0 at the very top of the jump. So we can rearrange and solve for Vy initial, which is 2.7 meters per second. Okay, that's your vertical speed. Okay, and because that's your initial vertical speed is 2.7 meters per second, you can actually use both of those, since the fact that your vertical speed is 2.7 meters per second. The horizontal speed is actually 2.7 meters per second too. And you can use a couple different ways. You can go Pythagorean theorem, you can go sine cosine to figure out that your initial launch speed is actually 3.8 meters per second. Now we're going to do a bunch of practice questions with a bunch of different situations in class. Make sure you look through your textbook. Make sure you look online about how to do projectile motion problems. And if you please come ready for questions. We'll talk to you in class.